Hi, my name is Laura. Hello everyone, we are a fifth semester chemistry students and today I want to connect and meet article with organic chemistry course and we take in our program. There in our organic chemistry course we study on the type of properties of aromatic compounds, cohesion, resonance and the effect of substituents of one reactivity and stability. And there is just perfect example of how the concept and appeal in the really scientific work. The scientists discovered that by combining acids with the carbons and doping them with carbon and nitrogen, these we are able to establish these molecules and also adjust their electronic properties. And this type of molecular modification is directly related to what the analysis organic too. And three, how electron distribution and resonance pattern influence the chemical behavior of aromatic systems. This shows how molecular length, stability, and electronic effects really directly determine the optical behavior of organic compounds. As chemistry and pharmaceutical biology students, we recognize the principles we study in a course aromaticity, resonance, stability, and functional group of the chemistry are not only theoretical technologies, but the basis of developing new materials and technologies that can transform both the science and industry.
Hi, my name is Jesus. Continuing I can add ascents have ionic optoelectronic properties, meaning they can conduct electricity and emit light. However, as these molecules get longer, they become unstable and react easily with air, light, or water, which has limited their use in applications such as organic, light-emitting diodes, or biological imaging. Until now, most ascents could only emit blue light. MIT chemists solved this problem by combining ascents with a special ligand called carbon and doping them with boron and nitrogen. This stabilized the molecules and allowed them to emit light in different colors from red to blue, depending on the length of the molecule and the attack chemical groups. In organic chemistry, we study aromatic compounds, conjugation, and electron dislocalization, all of which are directly relevant to ascents. The stability and light-emitting properties of ascents depend on resonance and electron distribution along the fused benzene rings by doping ascents with boron and nitrogen and adding carbon-dicarbene ligands. Chemists modify the electron density and resonance patterns will change the molecules stability and optical properties. This is a practical example of how concepts like aromaticity, substituent effects, and functional group chemistry influence in real-world molecular behavior.
Better stability. Another important feature of these ascenes is they remain stable both in air and water. Boron contains charged molecules with a low coordination number, meaning the central boron atom has few neighbors, are often highly unstable in water, so the ascene's stability in water is notable, and could make it feasible to use them for imaging and other application medicine. The researchers now plan to try incorporating different types of carbohydrates to see if they can create additional ascenes with another properties. Even better stability and quantum efficiency, a measure of how much light is emitted from the material. Gilliard also plans to work with Mark Baldo, an MIT professor of electrical engineering, to try incorporating the new ascenes into a type solar cell, known as single fission-based solar cell. This type of solar cell can produce 2 electrons or 1 proton, and making the cells much more efficient.
In the article read, the MIT chemicals have achieved a significant breakthrough in inorganic chemistry by developing stable ascenes and molecules that emit different colors of light. Led by Professor Robert Gilliard, the research team tackled one of the fundamental challenges in inorganic electronics, the instability of ascenes when exposed to air and light. These sheen-like molecules composed of fission-benzene rings have exceptional electronics properties that make them valuable as semiconductor and line-emitting applications, but their reactivity has historically limited their practical use. The innovation lies in the use of carbon-dicarbon ligands to stabilize and boron and nitrogen-dopant acids. This stabilization method allows the molecules to maintain their integrity in both air and water environment, a remarkable improvement over traditional acids that typically require end synthesis in the protect glove boxes. The resulting molecules can emit in red, orange, yellow, green, blue light depending on the length and chemical modifications.
Hi, I'm Brenda Jocelyn and I'm studying chemistry. And about the article, in conclusion, MIT chemists developed a family of boron-nitrogen doped acids established with carbon-dicarbonyls that can emit across the visible spectrum a rainbow of colors and remain unusually stable in air and even in water. This research shows how molecular design directly controls optical properties and how careful ligand choice can overcome reactivity problems in extended peace systems. For us, as a chemistry students, the work connects directly to several areas of the curriculum. One is organic chemistry. It applies concepts of aromaticity, conjugation, and substitution to tune color and reactivity. The second is inorganic organometallic chemistry. Carbon-dicarbonyls act as ligands, showing how coordination principles establish organic cations. The third is physical chemistry. The emission properties directly reflect homolume gaps, which you have studied in molecular orbital theory and spectroscopy. Another is analytical methods. Techniques like NMR, X-ray diffraction, and UVBs and fluorescence are used to prove structure and function methods we already encounter in labs. And finally, computational chemistry. DFT helps explain the stability and optical behavior, connecting theoretical coursework with modern applications. Why it matters? This research demonstrates the interdisciplinary nature of modern chemistry, bridging synthesis, spectroscopy, computation, and materials science. The resulting molecules have potential application in OLED displays, solar cells, and biomedical imaging, showing how fundamental chemical design leads to real-world technologies. For our learning, it reinforces that the theories we study in class, aromaticity, MO, theory, spectroscopy, and not abstract. They are tools researchers actively use to push the boundaries of science. And this is all about the article. We hope you like it.